You ever drive past a huge construction site, look up at a skyscraper or a massive wind turbine, and just wonder, how in the world did they get those giant pieces way up there? Well, the answer is usually an engineering marvel in its own right, the mobile crane. And today, we're going to go inside the incredible factories where these giants are actually born.
And we're not talking about your average crane here. We're talking about machines that can lift over 1,000 tons. I mean, that's like lifting 7 Boeing 747 airplanes at once. These things are the absolute beasts of the job site, and they somehow manage to combine all that brute force with pinpoint precision.
So, that brings us right to the big question for this explainer. How on earth do you even begin to build a machine that's not only this powerful, but can also pack up and drive down the highway? It's a pretty amazing story of steel, hardcore engineering, and just mind-boggling precision.
First off, let's just take a second to appreciate how crucial these machines really are. You know, these days, we don't always build from the ground up. A lot of the time, we lift massive pre-built sections into place. Whether it's the blade of a wind turbine stretching 150 meters into the sky or a whole industrial module, these mobile cranes are the muscle that makes it all happen.
Okay, so if you break it down, a mobile crane is basically 4 giant systems all working in perfect harmony. You've got the carrier at the bottom. That's the super heavy-duty truck part that gets it from A to B. Sitting on top of that is the superstructure, which is the whole rotating upper section with the brains and the cab. Then, of course, there's the main event, the telescopic boom, that massive lifting arm. And finally, you have all the support systems, things like the outriggers and counterweights that keep this whole thing from tipping over.
So where does a build like this even start? Well, it all begins with the foundation, the crane's steel skeleton. And we're talking about incredibly strong steel alloys that are designed to handle unbelievable forces without ever giving up.
And the process to create the skeleton is just meticulous. It starts with these huge plates of high-strength steel. They get cut down to size with insane precision using CNC lasers. Then, giant presses bend them into the exact shapes needed. After that, robots take over the welding to make sure every single seam is perfect. And to top it all off, the most critical welds are literally X-rayed to hunt for any tiny hidden flaws.
And when we say precision, this is the level we're talking about. The cuts have to be accurate to within 0.5 millimeter. The temperature of the welds is controlled like a science experiment to make sure the steel doesn't warp. I mean, any mistake here, at this early stage, is permanent. So perfection isn't just a goal, it's the only option.
All right, so with the skeleton built, it's time to give this machine a heart. The dynamic systems that actually let this enormous structure move and lift. And this is where that rotating superstructure really comes into play.
Right at the center of everything, you'll find this incredible component, the slewing ring. The easiest way to think about it is like a massive, super high-tech Lazy Susan. It's this huge, precisely engineered bearing with gear teeth all around it, and it's what lets the entire top half of the crane spin a full 360 degrees, smooth as butter.
But you know, it's so much more than just a spinning plate. This one single part is the main interface for every single load the crane lifts. Think about it. Every force, from the boom, the heavy load, the counterweights, it all gets funneled right through this ring. Its strength and precision are, and I mean this literally, the linchpin of the entire machine.
I absolutely love this analogy. If that steel frame is the skeleton, then the hydraulics are without a doubt the bloodstream. Instead of a bunch of clunky, complicated gears, almost every single movement, lifting, lowering, extending, it's all powered by high-pressure fluid. That's what turns hundreds of tons of raw metal into these incredibly smooth, controlled motions. And all that hydraulic power is what gives life to the crane's most famous feature, its absolutely incredible telescopic arm, or as it's properly called, the boom.
Now, the boom itself is a true work of art. It's built from these really long, box-shaped steel sections. Each one can be up to 15 meters long, and they're all nested one inside the other, kind of like a giant set of Russian dolls. This design is what lets the crane shrink down to a manageable size for road travel, and then extend to unbelievable heights once it gets to the job site.
And to push those massive steel sections out against gravity, well, that takes an enormous amount of force. We're talking about hydraulic pressures hitting up to 300 bar. To put that in perspective, that's over 4,000 pounds of pressure on every square inch. It's that immense force that makes sure the boom extends smoothly and stays totally rigid, even with a massive load hanging off the end.
Okay, so we've got the skeleton, we've got the heart, and we've got the arm. Now, let's look at the brains that control it all, the brawn that actually moves it, and the balance that keeps the whole thing upright.
Believe it or not, most of these huge mobile cranes actually have two completely separate engines. There's one big, powerful engine, sometimes up to 700 horsepower, and its only job is to drive the crane on the highway. Then there's a second engine, a real workhorse, that does nothing but power the hydraulic system for all the lifting operations. And that thing is thirsty. It can burn through 50 liters of fuel an hour just to keep the pressure up.
And just like it has two engines, it has two cabs. The driving cab down below is all about mobility. It's got your standard steering wheel and pedals, all designed just to get this massive machine to the job site. But the operator cab, up on the superstructure, that's a different world. It's the crane's real command center, a cockpit filled with joysticks and screens, all focused on one thing: precision lifting.
And inside that operator's cab, the single most important tool is the LMI, the Load Moment Indicator. You can think of it as the crane's digital nervous system. This computer is constantly processing thousands of data points every second: the weight of the load, the angle of the boom, everything to calculate whether the lift is stable. It's the system that prevents a catastrophic overload, and it's a perfect example of where data is way more important than just gut instinct.
So once everything is finally assembled, from the steel chassis all the way up to the computers, the crane still isn't ready to go. Before it can leave the factory, it has to go through one final grueling challenge, a series of tests designed to prove it's ready for the real world.
Now, to stay balanced while lifting something heavy, the crane relies on a huge stack of counterweights. During testing, this system is pushed to its absolute limit. On the biggest cranes, the total weight of the counterweights can be as much as 300 tons. That's like stacking dozens and dozens of heavy trucks behind the crane just to keep it from tipping forward.
And here is the most critical part of the entire testing process. The crane is deliberately loaded up with more weight than it's officially rated for, usually around 110 to 125% of its maximum capacity. This overload test is what proves the machine's structural integrity and verifies that its built-in safety margins are for real.
So in the end, this final test, it's not just a simple quality check. It's a guarantee. It's the final promise that this machine will be safe and reliable when it's out in the field lifting immense loads under the most extreme and demanding conditions you can possibly imagine.
From simple plates of steel to a high-tech precision lifting machine, the journey of a mobile crane is just an incredible testament to what modern manufacturing can pull off. It really makes you wonder, as our buildings get taller and our projects get more complex, what is it going to take to build the next generation of machines that will build our future?